Today we concentrate on improving the performance of one single processor, which initially have been built to execute one instruction after another instruction. We call it sequentially. Okay. The technique that have been explored long time ago, right? I think it's around 1970, right? And we call this kind of improvement pipelining. Okay, so we try to execute several instructions at the same time. Okay, so that the performance improve, right? Cycle per instruction reduce. Okay, that's the topic of today. This topic is divided into two section of content. One is the description how it works, and the second is the detail of the control step. Just like we studied the control of a single processor previously, simple graphical representation of executing instruction. Okay, so you can see 4 icon here. This one group represent one instruction going through time. Okay, and on the vertical axis is the one instruction A, and one instruction B, and one instruction C, and one instruction D. So also the vertical axis show the progress of each work, each job that you have to do. And this is ordering of the job, right? So to do job 1, and then you job 2, job 3, job 4. And the horizontal axis is the time. Okay, so it's a kind of what we call spatial temporal representation. Okay, you can see the whole picture, which job is done at what time. Okay, because there are several instructions, so there are several jobs, so to speak. So let's use example as a doing the laundry. We have to do it every day, right? Let us divide it doing the laundry into 4 smaller job. One is to put your laundry into the washing machine. Okay, and it run for a while, and then it finished the washing cycle. Then we put everything into the dryer, and then we take everything and throw it up into the stack of laundry, and then we carry it home and put it in the cupboard. Okay, so let's say each of them take some time, maybe to make it simple, equal time. Okay, so we do one batch of this, and then we have another batch, and then another batch, and another batch. So we have to do it 4 times. So it takes this much, okay, from left to right, okay, to do 4 batch. However, if we then stack each batch together, say we finish with putting the laundry in the washer, right? Once we put that batch into the dryer, we then start the next batch by putting the laundry in the washer. Okay, you may be able to recognize this as this 4 step of 4 machine, right? We do not have more than 4 machines, just 4 machines, right? But we try to use all the machine all the time. Therefore, this way, the total time suddenly become almost 4 times smaller. Okay, right? Okay, so how we do that with the real processor? Okay, well, let us break down the small operation when we execute one instruction into 5 steps. Okay, first one is we have to read the instruction from the memory, and second, we have to decode it at the same time. If you remember the data part, when we read the instruction from the memory, it also specify which register to read. Okay, so the second step is to decode and read the operand, read the value of the operand. That means read the register, and then we put that to arithmetic logic unit that we execute that instruction. Okay, if that instruction is a load instruction, and then it compute the effective address. Okay, so that's the stage 3, and then either it have to access the memory. Okay, if it instruction is a load instruction, then it have to read the memory, or if a store instruction, it have to write the memory. Okay, and if it's not the access to the memory, then it can do the next step, maybe writing to register, or that we call it write back. Okay, so read to value, compute using arithmetic logic unit, and then write the result back to the register. Okay, but if you do the load or store of instruction, then you have to perform access to the memory at the step 4. Just to remind you that we don't have to divide the step this way. Actually, Intel divided, I think the latest one divided into maybe 14 stage. Okay, so they're even more smaller step. Okay, then we show it here. Which is kind of intuitive to divide it in this way. Okay, and this is how RISC-V is organized. All right. For the illustration, we select only 1, 2, 3, 4, 5, 6, 7 instruction to show you how the pipeline works. Okay, these instructions are actually the representative. They are double load, double word, store, double word. Okay, which is represent the access to the memory. Okay, simple 64-bit data. And the next 4 represent the register operation, add, subtract, and logical, and OR. And the last one represent the branching instruction, branch if equal. Okay. Let's assume that the memory access, we have to assume that the time, the duration that used in each step, right? Divided into 1, 2, 3, 4, 5, right? 5, and the total time, the right handmost column. So let's start with the loading instruction. So let's say the instruction phase is 200 picosecond, very fast, and reading result is even faster, right? It's 100 picosecond, and your operation is 200, and data access is 200, and register write is 100. Okay, so it's total 800. Actually, this column, okay, if you recall, the actual main memory will be much slower than this. Okay, so this one is obviously data access to the special very fast memory. Okay, we will study that in the next few weeks. Okay, so just recall this number is a special memory. Okay, not the RAM that we can buy from the market. It's a cache, the high-speed memory built inside the processor. The same is true for the instruction fetch. In our presentation, we show the instruction memory as a separate from the data memory. Okay, you have to remember that. One crucial characteristic that make RISC-V run fast. All right, so there are several kind of instruction, and with a little bit variation in the total time it used. Okay, so if we are able to stack the instruction that way, what will happen? Well, you can make the processor run faster for a group of instructions. Let's say you run 100 instructions. So total is the total time of the non-pipeline or the normal, let's say the total time for each instruction. Okay. And if you have many instructions, you can sum all of them up, and then you divide it by the number of stage in your pipeline. In this example, it's 5. Okay. So it's 5 times faster. You probably, yeah, you remember the arithmetic on floating point, which contain many steps, right? Normalization, right, and divided the exponent part, right, and the right. There are many steps inside the floating point. You can imagine that those kind of computing unit is mostly almost begging to be pipeline. And we did that for all the floating point arithmetic unit. We pipeline them. And not only in the processor design, we can pipeline something like a hard disk controller, solid state disk, okay, and so on. So this kind of idea can be applicable to almost many aspects in computer system. Okay, how it actually work rather than for the laundry machine for the our processor. Okay, so we stack these 5 mini operation into one instruction. Okay, so instruction fetch, right? Reading register, executing by arithmetic logic unit, and access to data, and then write back to register. Okay, and they are written with the width according to the previous table. Right, so reading register is quite fast, right? 100 picosecond, and writing register quite fast. The rest is more or less the same. Accessing, reading the instruction memory, right? Perform a arithmetic logic unit, reading or writing the data memory 200 picosecond. Okay, a reasonable assumption. So total one instruction is 800 picosecond. So if you want to execute 3 load instruction, then it becomes 800, 800, 800, totally 2,400. Okay, this is non-pipeline, the previous presentation that we discussed before. Let's then stack these 3 instructions together. Of course, it becomes like this because the what we call the register, when you stack it with the next instruction, okay, of the fetching the second load instruction, the pipeline cannot be smaller, right? So we have to extend each stage of some mini operation here to be equal length, okay, so that the pipeline works, right? So we did it like this. Yeah, okay. So each stage become full to 200, okay. And then you can see that the last instruction finished at the 1300, okay, or you can say 1400. Okay, so executed just 3 instructions is already 2 times faster, right? When you think about how you design the processor, you have to consider 3 factors that make it possible to do the pipeline. First of all, RISC-V have fixed length instructions. So every instruction is 32 bits. So it just, when it read the instruction from the memory, it just read once, right? The instruction fetch, just read once. So it's fit into the first stage of pipeline nicely. Okay. You may think, well, that's okay, but what's the point? The point is other design may not be able to do this. For example, Intel instruction have variable length. Some instructions are very short, maybe just 1 or 2 bytes. Some, the longest one, 10 or more bytes. So the first stage, it has to read maybe 2 times, 5 times, 10 times, right? In order to do that, in order to pipeline the Intel, as I told you, Intel have all the processor that exist today, they all use pipeline. Okay. Intel actually change the instruction. When it read the instruction, it have a separate unit called what do you call instruction buffer. It read maybe 10 or 20 instructions at once, and then change everything into the fixed format inside the chip. Secondly, decoding the instruction is simple because the format of this processor is very simple. Okay. And thirdly, in the instruction set, only places that read and write memory happen is in just 2 instruction, load and store. Of course, there's some variation of load double word, load half word, and then that sort of thing. But anyway, let's simplify things and say it's restricted access to the memory only did 2 instructions, which make the arrangement of the pipeline, which you will subsequently see shortly. Okay, straightforward. Just the contrast to Intel, maybe, yeah, that's the processor that most popular has, I think, has largest number, yeah, of this processor in the world, okay, have been in use. So let's use that to compare. For the Intel, there's some instruction that can add the number, 2 number, one from the memory and one from the register together. So the access to the memory spread out so many instructions and make it very difficult to pipeline. Okay. When you stack instruction together, there's some contradiction, or something that limit that you cannot just stack everything with everything. Okay. So what are they? Right? We call it a harzard. Right? Yeah, kind of a technical term we use in computer design. There are 3 different types. One is structural. Structural is very simple. We don't have enough hardware to do that kind of thing together. Okay. Because our pipeline have the instruction fetch, and at some stage we have the read and write, read or write, not at the same time, of the data memory. Let's say if we arrange those 2 memory to be 1, okay, so just 1 block of memory can store both instruction and data. Okay, very simple idea. Then we will have structural harzard, because when we try to read the instruction, okay, at one instruction stage 1, some other instruction in the pipeline that want to read or write the data memory, okay, it will have the access to the memory at the same time, because two instructions want to access to the memory all at once. Okay, you say, hey, how we solve that? But that happened, right? We can solve that quite easily. If for RISC-V, they're just separate. So it's two memory, then okay, you can access 2 memory at the same time, no problem. For other, like mostly from the programmer point of view, we just see the single RAM, right? Not 2 separate RAM. So if it's a single RAM, then we can make that part of RAM that is connected to the memory, we call the high-speed memory or cache memory, to have 2 ports. So 1 block of memory that have 2 ports, that means we can read and write 2 locations at the same time. Okay, so we make the memory more complicated. Okay, so it can read two address or read one, write one at the same time. Okay, the multi-port memory, right? Okay. Secondly, we call data. One is the structure. Secondly, data. Data hazard is the dependency of two instructions. If you add one number, okay, to get a result, and the next instruction is use that result. For here we show these two instructions, add and then subtract. Because the subtract instruction use the result from the add instruction. In this is a register number 19. All right. If you think in the pipeline, the result have been produced and write back at the last stage. Okay. So the result will be in register number 19 at the last stage of the first instruction. And when is the second instruction want that value, for the subtract instruction, it read the register and feed that number to the ALU, right? So ALU have to have the value of register number 19 at the third stage. Okay, so if you align these two, then you can see that the result will be written in the fifth stage of the first instruction. Perform ALU here, right? And then memory data here, and then write back here. So X19 appear here, right? However, when we want the result here, the time, because this two instruction is stacking, right? You can see that how we can feed X19 to here. So this is definitely data hazard, because the required result haven't been available yet for the next instruction. Okay, so how to do this? Very simple. If we want to wait, then we can say, hey, let's store. We call this started a bit late. Okay, we can call it store by one cycle, and then we start here, instruction fetch, right? And here is the read register, and here we do the ALU, right? If we did that like that, you can see that it may be possible to if you start two cycle, then obviously it will be available, right? And so on. Okay, so this is what happened if we have hazard. We have to wait, okay, to delay the next instruction by one cycle, two cycle, before everything is ready to be used again. So, okay, this is called hazard and how we avoid it. One way is we can do we call this idea is to connect this unit to this unit. We call forwarding, which we will discuss later. Okay, forwarding, and the other way to call it, we call bypassing. The same thing. Okay, right? If we have the instruction at 3 register, okay, so we can break down each stage, right? The first stage is instruction fetch, and second is the decode, and right, and then execute, and the memory, and the write back. Forwarding do something. So now the result of the first instruction before writing back is already available here, right? Because it is the output from the arithmetic logic unit. what we have to do is to sense this result. Actually, if you are talking about the data part, we can have some wire going back, right, from the output of the ALU going back to the input, okay, of itself, okay. But it is now executing the next instruction in the pipeline. So you may be wondering, how did how it actually perform. Next week, okay. We at each stage we actually have the intermediate. We have a kind of extra register to store the result from each stage. We need that, otherwise we cannot do pipeline. Okay, we have three kind of hazard: structural, data, we are explaining it, and the control. Okay, let's continue. So we somehow we can send with special wire inside the data path to the input of the ALU that want to execute the subtract instruction. So you can forward like this, right? You need it here, okay? And before it even written back to register, we shortcut it here and send the result directly to the ALU for the next instruction. Okay, because once I finish this instruction, okay, I don't the first instruction do not need the arithmetic unit anymore. Okay, so it send the result and use the arithmetic logic unit for the second instruction. However, not every sequence of instruction can be solved without can okay can be avoid the stall, the delay cannot be avoided for all kind of sequence of instruction. We show you this example of the getting the data from the memory and subsequently use that value. Okay, so we load into x1 and then we use x1 for subtraction. You can see that you have to delay by 1, right? Because if you want to forward, this is already forwarding from, this is not from the you now from the memory stage, right? Because we want to use the data reading from the memory into to compute by ALU. You cannot go backward in time, right? Because this is, remember the horizontal axis at the time progressing. So if you want to forward it, at least it's the earliest it happened has to be here. So meanwhile, you cannot start this instruction immediately, right? Because you must forward here. So we have one delay, one stall clock. That means this clock, this one clock, perform no useful instruction. Okay, so reduce the performance a little bit. We want to reduce the number of stall. Okay. Okay, this diagram show you very clearly that some sequence of instruction cannot be avoided. Even though you do forwarding, then you still need 1 or 2 stall. We want to minimize this. Okay. One way to avoid that situation, load and then do something perform operation, we can reorder the code. Yes. Okay. To illustrate that, let us have this very simple 2 line program. Okay. A equal B plus E, and then C equal B plus F. Let's assume all the variable in the memory. Okay, so we have to load B and E using these two instructions, okay, into two register, and then add them together here, okay, and then store them afterward, okay, and then we do the same, and then we load another, which is F, right, and then add it to B already in the register, okay, and then we store it to the destination, okay, right. With this sequence, load, add, store, load, add, store. Very straightforward, translated from this one. If you draw the diagram, okay, the space-time diagram that we talk about, okay, you will notice immediately that there will be some kind of storm. All right. So let's move the last load the variable f. That I scroll slowly back. Okay, this one. Okay, move outward. Okay, to avoid that store. Go to here. Then the pipeline will be one less store. Who is going to do this? Well, you can do it two ways. One is the compiler, okay, can reorder the instruction for you because it generates the code, right? Then we can, if we know about the pipeline stage of the processor, which actually you can make the compiler to be so clever like that, so it can rearrange. For Intel, it uses the same because it have the reading instruction buffer. It can use the hardware itself to reorder the instruction. Yeah. Now to the final section. The third type of hazard is when you have to decide, this is obviously the branch instruction. You have to decide whether you want to branch or not to branch. Most of the conditional branch take the result from the register. So what happened? The result, if the branch follows some kind of calculation, okay, and then they want to use that calculation, it has to store. Of course, right, you can see the situation immediately. It's already available here. Okay, the result of the decision. Branch equal mean if x, let's assume maybe register 19 is 0, then it try to branch. Okay, I'm not quite sure about the effect of this, but to illustrate that, however, here it need to know the next program counter, right? So it cannot make decision because the result is, even though we want to forward it, because the result already appear here, you still have to wait here, right? So in this sense, it's actually store for two, right? Two slot. Right? Store because each small step one cycle. Okay. This is what happened, and we call that control hazard. How we solve the control hazard? We have this magic, right? We can foresee, we can predict whether we want to branch or not to branch. So we call that unit branch predictor. I think if you can predict, if at that time you know, right, that the branch will be taken or not taken, then you don't have to store at all. Okay, there's a way to do this kind of prediction. The big picture, okay. before we get into that, performance improvement of the pipeline equal to number of the stage. Okay, so total non-pipe divided by the number of stage in pipeline. So that's the big picture. And there's two measurement. One is how many instruction it can execute in a period of time. We call that throughput. How much you can get the job done. Okay. And the second is latency. If there's the one job come in, how fast it can go out, we call latency. Okay. Latency and throughput, although go together, is a separate way of measuring. Okay. If you want quick response, then you need low latency. If you need a lot of work done, okay, then you need throughput. Of course, if you have low latency and high throughput, that is the best.